that, I want to talk about the complexity, right? Those computer science guys just left. They know the best, and this is the most difficult part. What we are doing was just here in this class, we do qubit by qubit. We try to familiarize ourselves with the detailed operation. But when you go to how to prove that the oracle is going to work, how to prove that it's possible to construct something in a reasonable time, you need a lot of mathematics and computer science complexity theory, right? We only say something very simple, right? Just want you to, some of you to understand if you have not heard of that before, right? So let's just think about, for example, in an addition operation, right? Let's say it takes 1 second to add one digit. For example, let's say I have n equals to 3. There are 2, 3, 5 plus 1, 2, 3. We ignore the carry. How much time do I need to do this addition? 1 unit of time, 2 units of time, 3 units of time. Make sense? Right? So this is just a simple, not rigorous example, right? So it means that, so case 1, if I try to write it time, right, the number of digit and then the time I need. If n equals to 1, then I have 1 digit. Then I need 1 unit of time. If I have, let's say, 100 digit, how much time do I need? Maybe I should just remove this. How much time do I need if I have 100 digit? 100. If I have 1 billion digit addition, how much time do I need? 1 billion units of time, right? Now here, you need to be careful when people discuss this, not even for complexity theory. You don't only talk about time, you need to talk about hardware. If you have 1 billion calculator at the same time, you only need 1 unit. Okay, so here we don't talk about different number of hardware. We assume we only have one hardware. Make sense? Okay, so this one grow up linear with time. Then we say this is the complexity is in the order of n, capital N. Now, when we say this, we means that the difficulty go up linearly with the size of the problem. Now, you may say, there's some overhead. I need to load it from memory, or I need to do something else, whatever. But those who overhead might be constant, or they grow slowly than the n, right? For example, square root of n, or a log n. Then your mean time is still related to n, right? Because if you need 10 to the power 9 years to finish something, even you add another 1 million years is meaningless to me. The order is still 1 billion years, right? 1 billion and 1 million years is as long as 1 billion years for me in terms of computational difficulty, right? And that's why we will abstract to the highest order one. But in real calculation, we will see some difference. We need to consider. But anyway, here we say the complexity is n. Okay. Now, case 2, let's say you invented some method to do the digit faster, and we don't discuss how. And if I have one digit, it takes square root 1 equal to 1 unit of time. When I have 100 digits, it takes square root 100 equals to 10 units of time. When you have no, this is not a good one. Billion digit, it takes 10 to the power 9 over 2 units of time. Okay? So this is very different because at the beginning, we are pretty similar, right? We try to compete. Well, your method, we also all take 1 unit of time. And actually, you might take more time than me because your new method might involve some preparation of the data. Or on other sense, or also in the other hand, when we have 100 digit, I need 100 units of time, maybe 100 seconds. And you only need 10 seconds. Maybe I also don't care that much, right? 10 difference between 10 seconds and 100 seconds may not be a big deal for my life, right? But later, when we're doing a big problem, I need 1 billion seconds, and you only need 10 to the power 9 over 2 seconds, which is how much? 100,000, 300,000, right? 300,000 seconds. That is completely different. Because 300,000 seconds is what? Maybe about 300 hours, 100 hours. But 10 billion seconds is talking about maybe years, 10 years or more. Now, that is a big deal, right? You see the big difference. So this one, we say that the complexity is the order of square root of n. It can be this. It can be the real time can be equal to square root n times maybe 2 times 2 is okay. And then plus 0.5 and then plus maybe log n. Can be something like this. But what I care is that when n is very large, 0.5 is not important. Log n is not important. Right? Sometimes we put 2, sometimes we don't put because 1 billion years is the same as 2 billion years for me. I just cannot live that long. Right? In that sense, you feel that order of magnitude? Or when you bring this solution to your customer, you say, well, this problem is supposed to solve originally is 1 billion years. Now I shortened it to 500 million years. They are still not going to buy your product because it's still useless for them, right? Just a very time constant difference, right? So that is another case. Now, let's say you get very smart, you come up with something even better. When you are 1, you basically take no time. You take log 1, you go to 0. But this is not important. When you have 100 digit, right, you take log 100, which is 2. When you have 1 billion digit, you take log 10 to the power 9, which is 9. That is a big deal. Right? Now I make 1 billion second problem becomes 9 seconds, not 300,000 seconds. Right? So this one, we say it has an exponential speed up in the order of log n. So what we are going to see in this class is that we will see algorithm that quantum computer provide a square root speed up, which is the Grover's algorithm, or logarithmic exponential speed up, which are the Shor's algorithm for encryption and decryption. Okay? And of course, we need to say something very important. Now, if I try to plot this on axis, and let me call this n, and this is the time to solve it. Maybe you have this this is n, order of n, go straight line. Okay, we also have something called exponential, right? But let's take this as the benchmark. You actually might have something like this for square root n. Now you will see that at the beginning, usually that is the case. Now, you don't get things for free. For small problem, yeah, you have this method to do things in square root, you actually have more overhead. So for small problem, you actually spend more time. I hope you understand this, right? But if you go to logarithmic, you actually might have something like this. So I did not draw it well. It has even more overhead. Okay, but it grows much slower as a function of n. And it will take a much larger sample in order to break even. Okay, so basically, for example, in Shor's algorithm, it provides exponential speed up. But if you ask it to do a very simple factorization of 21, which is 3 times 7, even elementary school can tell you, oh, 3 times 7 equals 21. They can calculate very fast. Classical computer can do it very fast. But quantum computer actually should be slower than that by a lot because of a lot of overhead, state preparation, and you do a lot of measurement. Actually, later you see that you cannot get the result in one shot. You need to repeat the calculation many times, and it has a high probability to give you the right result. So the overhead is large. But when you start increasing the number of bits, let's say to RSA encryption, like 1,000, for how many bits? 1,000 bits, 1,000, what is that? 1024 or 2046 bit, right? Then that will take classical computer maybe for 1,000 years to solve it, right? We all rely on this because we assume that we don't have supercomputer that can factorize the number within maybe 1,000 years, and that's why we do this encryption, right? But the quantum computer is going to take a lot, 1,000 years. Right? I don't know the scaling, maybe it means 3 years or 3 months, depends on the overhead and scaling, but it won't take 1,000 years. Right? And that is how you get better, okay? Any questions about this complexity? You will see this very often, right? But you don't need to be able to calculate the complexity, right? I think in computer science class, they have a course just for algorithm and complexity. That actually is very difficult for me. Okay. But we just take it for granted. This one we skip. So now we start with a new algorithm group. It is the Griffith's search algorithm. And for every problem, every algorithm, you should know what problem it is going to solve. So we assume with n, capital N, you are 2 to the power n entries. Okay, you are going to search something, okay, of unstructured data. What is the meaning of unstructured data? Database. So for some database, they are sorted already. Let's say the database of the student at SJSU, right? We sort it by student ID, we sort it by last name. Because it's sorted, it's structured, I can find someone very easily. Now in classically, you can use so-called bubble sort, not bubble sort, but as binary search, right? Because I sort it, I just go to the middle and see, okay, this last name has a alphabet after me, after the one I'm searching, so I just look at the first half. I don't need to look at the second half, right? And I keep doing this binary search. Let's say I can do it in logarithmic speed, right? For those who have taken computer science algorithm. But this is unstructured. So there's no information. Then how do you search for someone in that case? How much time do you need? I want to find x equal to a, where f of a equals to 1. But if x is not equal to a, then it equals to 0, right? What is the meaning of searching? You are doing computation after all. I want to search for my entry, right? I will compute my ID against the ID I gave it. I do a subtraction, equals to 0. Then this is me, right? If I see your ID, I subtract my ID from your ID, it is not equal to 0. Then I know that is not the entry I'm looking for, correct? So this is a computation, and the computation will be very expensive. Let's say image mapping. So how much time on average I need to find my record? If I give you something unstructured, right? Like when we finish midterm, if I return the midterm paper to you and I say, find your own paper, how are you going to find it? On average, how much time would you need to find it? You need to go through everything. If you are, okay, you say half. Why? Yes. Exactly, automatic. Because when you are lucky, you find it, oh, mine is on top. I must be, I don't have the lowest score, or highest score. That's why Professor put it on top, right? Or if you're unlucky, you need to find all of them. You find it at the last, right? So on average, but it's true, we need to search all of them. Need n over 2 search. Or in other words, computation. I need to do n over 2 computation. So you have a 1 million record on average. I need to do 500,000 computation, which is a lot, right? For 1 million records, right? This is, but quantum computer will give me an order of square root n. So 1 million record, I only need to do 1,000 computation compared to 500,000. Okay? And more exactly, it is pi over 4 square root n. Okay, so in order to search a record, I only need to compute pi over 4 square root n, which is about square root n. And that is the so-called Grover's search algorithm. Okay, so do you understand the problem now? The problem is that we have a large unstructured database. I want to find a record. So when I find it, it's a computation process. Classically, I need n over 2 search or computation. But quantum mechanically, in quantum computer using Grover's search algorithm, I only need square root n time of computation. And you can imagine, again, we will use superposition. Okay, so this may be a little complicated, but that is okay. But first of all, let's look at the quantum oracle, an example of quantum oracle for Grover's algorithm, right? Again, how do we really construct this is not what we are going to discuss. What we're doing now is that just to say that if we want to do a simulation or try to appreciate what is the meaning of the oracle in a Grover's algorithm, okay? So for example, I want to search A equal to 10010, right? This is the problem, right? It's not a function now, right? Or you can say a function, it's a function, right? But the problem is that I want to compute f. Basically, the goal is this. I should restate it, right? The goal is that goal, right? Is compute f of 100. Compute a function that x equal to 10010 will give me 1, and then x not equal to 10010 will give me 0. This is a function, okay? It takes integer input, always output 0, unless x equal to 10010. Make sense? If I can compute this function, then that is the searching process that I want. So in this case, A equal to 10010, what I want to search. How many qubit do we need? What is the number of qubit? I call it qubit because I already assumed that we're going to encode this as the basis state. So how many bits do we have here? 5. Yeah, very simple, just 5. Okay. So what is the number of entry that 5 qubit can have? 5 bits can have? To the power 5, 32, right? So this is a 32, a database with 32 entries, and I want to search an item that is when A equal to 5. Okay, so how do I construct it? So on the right, I already show you how it is constructed. So this is a exclusive or quantum oracle. This is exclusive or quantum oracle. with UF x y equals to x y exclusive or f of x. Now let's see if it makes sense. First, this x, right? It must be 5 qubits because we are searching a database of 32, right? So I have x0 to x4. And then what is y? Y is related to the output. Y has 1 qubit because it's related to f of x. F of x is either 1 or 0, right? This is only need 1 bit because the result is either 1 or 0. So the whole oracle will have 6 qubits. Right? So if I draw it, it will be something like this. X, 5 qubits, Y, 1 qubit. Output is still X, and this will still be Y, but this is going to be X, Y exclusive or f of x. Is this okay? And of course, this time I put the top as MSB because the x is on top. Right. So this is the quantum oracle that I have. And how do you really implement this function? Because this function is tied to A, right? It means that if my input is 10010, my output f of x should be 1. So let's check if this is correct. This is, I gave this to you, right? But so let's check if this is correct. Now, first of all, x come in will be 0, 0, 0, 0, 0, 0. Okay? Yeah.
That x, y, x, f of x is 2 qubits, right?
Which one?
Yeah, that one, yeah.
Y 2 qubit. This one should be 2 qubit?
No, you said the output is 1 qubit, but
Output is 1 qubit, yes.
But that's kit x and y exclusive RF of x, that's 2 qubits, right?
No. So I only have one number here, right? That's a good question. This is y exclusive or f of x. This is completely classical, right? I'm doing a exclusive operation. If you're 2 qubit, I mean let's say 1 exclusive or 1, it gives you 0. 1 exclusive or 0 give you 1. Do you see? This is just a mathematical operation. Yeah.
So that's the total output I'm setting, not just the
This whole thing is the total circuit, yes. Because I don't, yeah, maybe I should put this on top as x, and then I see why I'm confused you. Yeah, so I just put the total, but I can also put it as this. Does that make sense? Okay. So let's continue to the tracking, right? So at this stage, what is this? 0, 1, 1, 0, 1, 0. Is that okay? After the NOT gate. What we, yeah, of course, sorry, I say completely wrong. I'm sorry, I need to erase it. I say something wrong. I say something wrong. Sorry, this is wrong. It's not 0. I don't have a cheat sheet, but now I. So now let's say the input is A. I'm sorry, right? Let's say A. A is the input. A is the input. So when A is the input, this is 1, 0, 0, 1, 0. Are you okay with this? And then Y, we will just do it with 0. Okay. After this, what do you get here? You get 1, 1, 1, 1, 1, 0. Make sense? Because of the NOT gate here. See, why is not NOT? It's still before the NOT gate. I'm talking about right before here. This 9. This one? This one? Oh, because this is A4. So 1, 0, 0, 1, 0, 1, 0, 0, 1, 0. Okay. These are all 1. Can you guess what type of gate is this? Very good. So we have learned control NOT. We have learned Toffoli gate, control NOT. And this is like you, yeah, that's good. We have 5 fingers. So this is like control NOT. Okay? Control 5 times. What does it mean? What is the meaning of this 5 times control NOT? You only flip it if all 5 are at one state, right? And that's why now it's all at one state, right? So we are going to flip it and this becomes 1. Okay? And then the rest is just to, we can say decode it. This is 1, this go back to here, this go back to here, this go back to, this go to 1, this go back to here, which is again equal to A. Do you see that? And so this one makes sense because the quantum oracle say that input is X, outputs need to be X. So this is a valid quantum oracle, right? X, X. But the main point is because now this becomes 1. And now what? And then I claim that this equal to Y exclusive or F. Exclusive f of x, is that right? Because y is 0. What is f of a now? Because I input a, right? What's f of a? 1, right? So indeed, this is equal to y exclusive f of a. So this quantum oracle really did this function. Now you can go back to check if this is not a other value, you will still get the x out because this will just uncompute. You can call it uncompute, right? So whatever goes in will come out. But this one is not going to become 1 because it is 0, right? And because it's 0, then y is 0, then your output is 0, which is still correct because by definition, you want to have 0 because f of x not equal to a is 0. There's a little bit confusion here, but what do you mean the same? Which part is the same as Deutsch algorithm? Uh-huh. The quantum oracle behave exactly the same. You are right, because we use exclusive or quantum oracle. Here is just the oracle. I show you how to construct an oracle by example, but we have not gone into the algorithm yet. The algorithm, you will use this quantum oracle to perform the search. Good question. Yeah. 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 Yeah, very good. So our goal is this. We want to show that this circuit will give a value in y equals to y exclusive f of x, right? If this value does give this, then we say this is a correct oracle, right? So now in this particular case, our input is x equal to a, and I got 1 here. Make sense? I already showed you that I get 1, right, when the input is a. Okay, then what is y exclusive f of a? Because this need to be equal to y exclusive f of a. If they are the same, then it means I have implemented the function y exclusive f of a. For the oracle to be valid, this 9 need to output y exclusive f of a. This one, okay? Okay, so let's don't go to here. What is y exclusive f of a? It is 0 because my y input is 0, right? And f of a by definition is it need to give me 1, right? Because when you are if your entry is a, then f of a equal to 1 because you find the entry you want. So y exclusive f of a is just equal to 0 exclusive 1, which is 1, right? And then now I show you that, hey, I also get 1 if I use this circuit. So then it means this circuit is really computing, is doing what I want here. Yeah? You're right. I would, not me, of course, it's from textbook. We just show that if I have an oracle like this, it's really implementing the problem I want in this oracle, right? But how do you come up with this? That's if when you don't know the function, because you really don't know what you, yeah, this is another problem. But here just to show you that they are consistent. Okay, so we only have the oracle. Then we will do the Groover's algorithm, right? But because of time, I better do it next time. But that is not a problem. But just a quick overview. You are going to encode what you want to search as X, your target as A, and then you create some other vector, including a superposition vector, right? And then you will go through this flipping. Eventually, you will find the answer. Okay, but we will discuss next time. Okay. Let's stop here.